Okay, now it's time for the case B or question B. We are talking about line-to-line fault, okay? We are talking about line-to-line fault. What is the terminal condition for this? What is the terminal condition for this kind of faults, line-to-line faults? Well, if you remember, we have the three-phase system, and this is the point F, and we are assuming that the short circuit is between B and C. If we have a short circuit between B and C, and we are considering a fault impedance equals 0, that is a volted or solid fault. In this case, of course, in this case, we have some terminal conditions. And the terminal conditions are the following. The current in the line A is equal 0, because if you remember, this system is under non-load conditions. There is not current before the fault, and the current A is equal to zeros. Extremely simple. But if we use a voltage fault, the terminal condition is that the voltage here, B and C, this is the short circuit, and this voltage is equal to this voltage, the voltage B equal to voltage C. And finally, the third terminal condition is the current here is equal to minus the current going here. What I'm telling you is that the current B is equal to minus current C. And that is the third important terminal condition, okay? Well, if you remember my classes from the theory of symmetrical components, all my students, I am sure that they must remember that for the line-to-line short circuit, the positive and negative sequence networks, they are in parallel. They are connected in parallel. And that is what I am showing here. This is the positive sequence network. This is the negative sequence network. And over here, you can see the zero sequence network. A very important conclusion from here, the zero sequence current is equal 0. That is a straightforward conclusion, and all my students must remember this, because if the short circuit is not involving the neutral or grounding point, there is not zero sequence at the short circuit current, okay? That is very important, and you must remember that. If the short circuit is not involving ground or neutral, there is no zero sequence here at the fault, okay? Well, now what we need to do is basically use circuit analysis. And as you can see, those networks, they are in parallel, but we can calculate the positive sequence current very easily. The positive sequence current here, the positive sequence current is basically the voltage divided by the total impedance. And this is the positive sequence Thevenin impedance, and this is the negative sequence impedance, and that is this equation over here. Positive sequence is the total voltage divided by the total impedance. And my students, they are extremely clever on circuit analysis, and they must remember that here the positive sequence is equal to minus the negative sequence, and that is what I am telling you here. Okay? Well, this is circuit analysis. My students can use the calculators, they can use MATLAB, they can use Python if they wish. You can use any kind of calculator as you want, but at the end, what I want to get is the positive, the negative, and the zero sequence, okay? And as you can see here, this property is fulfilled here. You can see that the magnitude of the positive and negative sequence, they are the same, 1.559 per unit. The magnitude is the same. What I'm telling you is that the magnitude of the positive sequence is equal to the magnitude of the negative sequence. And all of them, both of them, they are equal to 1.559 per unit. That is clear. And also what is clear to all my students, it's the 180 degree, and this is this property over here. Positive sequence is minus negative sequence, okay? What we need to do is, this is the currents from positive, negative, and zero sequence, and we need to translate that into ABC. To transform 0, 1, 2 into ABC, we use this matrix A, and that is the transformation matrix. That is this matrix over here, okay? This is the matrix A, and you must remember that A, lower letter, is 1 at 120 degree. That is a complex number in polar form, okay? Now, what we need to remember, the zero sequence current is 0, and the negative sequence is minus the positive sequence, something very simple. And then my students, they use the calculator, and they calculate and obtain here current A, current B, and current C. And what is the very important conclusion here? If you remember the terminal condition from the very beginning of this problem, current A should be 0, and current B should be equal to minus C, and that is happening here. If you look this complex form in polar representation, you can see that the magnitude is the same for both phasors, but you have 180 coming from this negative sign over there, okay? Well, but this number is extremely nice, but again, this question is not about per unit. This question is about amps. And the amps, they can be calculated multiplying those per unit values by the proper base. In this case is 100 MVA and 66 kV, and the current base is 874. And if we multiply these per unit values using this base, what we obtain here is the very important short circuit current. And as you can see over here, the magnitude B and C, they are the same, and the magnitude is 2.3 kiloamps, okay? This is very important. B and C, the magnitude is the same. Sorry. And the magnitude is 2.3 kiloamps, okay?